Okay. Well, so I guess the one thing about this one is you have to recognize that you know the acceleration of this body because it's just hanging there. It can't go anywhere. And so you know the acceleration is 0. Other than that, I mean, in a way that makes the problem easier because it's one less thing to calculate. So you want to draw the free body diagram. And then every force in the free body diagram goes on the left side of the equation. Set the acceleration equal to 0, and you can solve for the forces. Okay? Any other homework questions? Yeah.
It's like 4
On this assignment that I have up?
Yeah. Right
Yeah. When is this due?
Next Monday.
Next Monday. Okay. We are getting to this stuff today. So that's the next thing. We just haven't talked about that yet. Okay. Well, remember that lab exam 2 is next week in lab. Okay, so where we are in the class is we're talking about the 3 different special cases where you have to have sort of special strategies for Newton's second law problems. So I'll call it 3 specific cases for Newton's second law. It's not that you couldn't think through these 3 cases with the regular stuff, but it would just take some time, and these turn out to be pretty efficient ways to approach these kinds of problems. So the first one is collections of bodies with the same acceleration, and we talked about that last time. The second one is rolling and sliding problems on inclines. And then the last one is collections of bodies with different accelerations. We've done this one so far, so now we're going to talk about rolling and sliding problem on inclines. And so, I mean, in a way, there are really only 2 kinds of inclines you can have. You can have one facing this way, or you can have one facing this way. Bless you. Okay. And in both of those 2 cases, we are always going to use so this is a new thing that we haven't done yet in this class. We're going to choose a coordinate system that makes the math easier on this. And the coordinate system we're going to choose is always going to have the y-axis pointing directly out of the surface. Okay, so the y-axis is going to point this way and this way on the other one. And in order to make this coordinate system meet the requirements that we have, it just has to be like a rotated version of the standard coordinate system. So x has to point this way here, and it has to point this way here. So the y-axis is always going to be out of the surface. And that means the x-axis is always going to be along the surface. And the first question is, why are we going to do this? There's no reason we have to do it. There are ways you could solve these problems without rotating the coordinate systems, but it makes the math easier. So it just makes the math simpler. And so I just want to point out the things that I sort of want to do a cost-benefit analysis of, like, what are the things that get easier? What are the things that get more complicated? So you can see that this works in our favor. So let's say over here, I'll put the benefits. And over here, I'll put the drawbacks. And I'm just going to go through the different kinds of vectors that we have to deal with in this sort of problem. So first, there's going to be an acceleration. Okay, you always have to deal with an acceleration vector. If we used, so how can these things accelerate on these inclines? They can only move along the surface, right? But the surface isn't horizontal anymore. So if we used a standard coordinate system where the x-axis was horizontal, we would have to use cosine and sine to figure out the direction of the acceleration. That would be kind of, not impossible or anything, but makes it a mess, okay? So one of the benefits of using this rotated coordinate system is the acceleration is just always going to be a0. Nice and simple, okay? Since the x-axis is along the incline, we can always just say it's along the x-axis. Now there's always going to be a normal force, a pushing force from the incline onto the object. That normal force is always perpendicular to the surface. So again, on an incline, that would have x and y components. You'd have to use sine and cosine to figure it out. It would get messy. But with the rotated coordinate system, this is always just going to be 0n. And then the friction force, there isn't always friction in these problems. In the two examples I did where there's wheels, we wouldn't include friction in the problem. But in sliding problems where you have friction, the friction is always along the x-axis, either positive or negative. Well, it's always along the, I said the x-axis, is always along the surface, either to the left or to the right. if we had the x-axis horizontal like a standard coordinate system, again, we'd have to use cosine and sine to represent the friction force. But with this rotated coordinate system, the friction force is just going to be plus or minus mu times the normal force in the x direction. Okay, so all three of these things are nice and clean with the rotated coordinate system, and they'd be messy in a standard coordinate system. Okay, there is one thing that gets messy in this rotated coordinate system. It's really the only thing that gets confusing about this. In the standard coordinate system, the weight force has always been super simple, right? It just points down, so it's in the negative y direction. Now in this rotated coordinate system, notice it doesn't line up with the x or y axis anymore. So the weight force, this is the one drawback. We're going to have to represent this as the magnitude of that weight times the cosine of some angle. I'll call this angle the Greek letter phi. And then mg times the sine of some angle. But if you have the choice between three simple things and one complicated thing, or the opposite of that, one complicated thing and one simple thing and three complicated things, it's pretty clear why we're making this choice, to use this rotated coordinate system. We're simplifying a lot of things, only giving up one thing in the drawbacks column. So I want you to notice that angle phi that we're using in the weight here. So phi for calculating the weight force is always just 270 degrees plus or minus some angle theta, where theta is the angle the incline makes with the horizontal. So your job really is just figuring out, are you going to add the angle or subtract the angle? So the trick is figuring out whether to add or subtract. Okay, so let me draw two pictures and sort of show you what I'm talking about. So let's say that we have an incline like this. Let's say this is 15 degrees. And we have this object sliding along this surface. That coordinate system is like this. The weight force is straight down. So if I draw the coordinate system, and here's the weight force, the question is the angle from the x-axis to the weight force vector less than or more than 270 degrees? That's what we're always trying to figure out.
So you could put the y-axis in it.
You can put it anywhere. Yes, all that matters are the directions. That's right. But you always have to go, that coordinate system always has to be just a rotated version of the normal one, you know? So if my y-axis is going this way, I can't have my x-axis like that. You'd have to flip it to do that. Okay, so what's this angle phi that we're going to use to calculate the weight force vector? Well, always to come up with vector components, you're figuring out the angle that goes from the positive x-axis around to the vector, okay? And to figure out whether you're adding or subtracting from 270, just figure out in this arc that I've done, have I gone past 270 or not made it to 270? In this case, I haven't made it to, so this angle phi is 270 minus 15, or 255.
Wait, why is the force pulling down?
Why what? That's the weight force vector, and weight always points straight down. Any other questions right now? So let me show you one that's the other way, and it's just the other way that an incline can face. So let's say this time this angle is 20 degrees. The coordinate system, draw the y-axis pointing out. X is along the surface. And now I'm going to draw, so here's my coordinate system. Here's my weight force. To get from the positive x-axis to the vector, you go around like that. So this time is phi less than 270 or bigger than 270? Bigger. I had to go past that negative y-axis, you know? So phi is 270 plus 20, or 290. Okay? All right, well, let's really, I mean, that's the trickiest part of these questions, is just figuring out how to represent the weight force. Once you do that, everything kind of follows the rules we've already talked about. I'll do one without friction, and then I'll do one with friction. Okay, so let's say this is 20 degrees. And we have an object rolling along the surface. And let's say that this has a mass of 10 kilograms. What's the acceleration of the cart? My coordinate system has the y-axis pointing directly out of the surface, x along the surface. And so, you know, in these problems, you always have to deal with this weight force vector. We might as well figure that out first. We know we're going to have to get to it eventually. So I'll put that over here. Let's think about that. So the coordinate system is this. The weight force is this from the positive x-axis to the weight force vector, is that counterclockwise angle, is it going to be 270 plus 20 or 270 minus 20? Plus, exactly. So phi is 270 plus 20 or 290. And so then the weight force is, well, I guess I'll put that in when I write out Newton's second law. So let me draw the free body diagram now. We have a weight force. The magnitude of the weight force, the rules are exactly the same as in everything else. The mass of 10 kilograms times 9.81. So this is 98.1. Now go around the boundary looking for contact. There's a pushing contact with the surface. That's perpendicular to the surface toward the chosen body. So there's the normal force. I tried to draw these carefully so you could see that those are not parallel to each other. And there's no other contact, so that's it. And so now we can go to Newton's second law. The normal force always shows up as 0n. That n is always in the direction of the positive y-axis. The weight force is 98.1, that weight we have there, times the cosine of 290, and 98.1 times the sine of 290. And then these are equal to the mass times the acceleration. And I'm always just going to write the acceleration as a0. So let me calculate out those components of that weight force. 98.1 times cosine of 290, 98.1 times sine of 290. So I can write this as 0n plus 33.55 negative 92.18 is equal to 10 times a0. We're trying to find this acceleration vector that we know is a0, which means the only thing we have left to figure out is the value of a, and then we can plug it in there. So all I have to use is the x component of this equation. And that says 33.55 is equal to 10a. And so a is equal to 3.355 meters per second squared. So the acceleration vector, now you can plug that value back into this vector, is 3.355. Or another way to write this is 3.355 in the direction of our positive x-axis, which is down the ramp like this. Any questions about that? Remember that A can be positive or negative. The math will tell you what direction it's in. So there'll be other cases where you'll get an a value that's negative, and then you'll have to plug that negative value into the vector to get the final direction. Yep.
So if the arrow is straight down every time, how do you know when it changes, like when it's more or less than 270? Always just
Okay, yeah, because the key thing is that, remember when we did the vectors assignments, that the way you figured out what to use with cosine and sine is you start at the x-axis and go to the vector, you know? Well, the negative y-axis is the 270 line. So if your arc of your angle goes past the 270 line, then you know you have to add. And if it doesn't make it to the 270 line, like in this case, then you know you subtract. Okay. So that's why this one is less than 270, but this one is more than 270. Yeah.
How did you become straight on the 0.55 to 3.55?
See that x equation? In order to solve for a, I just divided both sides by 10. Any other questions? Okay, so that's how you do a problem that doesn't have friction. Then you also can have sliding problems that do have friction. So let's do one of those. So let's say this angle is 30 degrees. And there's a block, let's say it has a mass of 2 kilograms. And let's say the coefficient of friction between the block and the incline is 0.1. And we want to calculate the acceleration vector again. Before this is a complete problem to ask, I need to give one more bit of information. Anyone remember what is it in a friction problem that I haven't told you yet that I need to?
the direction.
That's right. I need to tell you which direction the velocity is at this instant. So let's say that at this instant, the block's sliding down the incline. And since in these kind of problems, I have to tell you the direction of the velocity, and we're able to calculate the acceleration, in these friction problems, I can ask you whether the thing is speeding up or slowing down too. So let's calculate that. Is this speeding up or slowing down? So if we find out that the acceleration is in the same direction as the velocity, it'll be speeding up. If it's in the opposite, it would be slowing down. Okay, let's compare that to the one we just did. Is this one speeding up or slowing down? We know the acceleration is down the ramp, but we can't answer that question unless someone tells us the direction that the velocity is at this instant, okay? The reason is we can do this whole problem without knowing the velocity, so it just doesn't have to be given to us. The answer for the acceleration is the same no matter which way it's rolling at that instant. If at this instant it was rolling up the ramp, it would be slowing down at the rate that we calculated. If at this instant it was moving down the ramp, it would be speeding up at that rate. Okay. Okay, well, let's do the same thing again. Let's figure out before I get into the equations, let's figure out the angle of the weight force vector. So the coordinate system looks like this. The weight force vector looks like this. to get from the positive x-axis to the weight force vector is like this. So is it more or less than 270? Less. And so our angle phi that we're going to use is 270 minus 30, or 240.
If only when it hits the Y.
Yeah, if you, if this coordinate system was tilted the other way, this line would be on the other side of the negative y-axis. And then to calculate that angle, you'd have to go all the way past the y-axis. In this case, you don't have to go past it because the vector is on the left side, you know. Okay, so now free body diagram. There's a weight force down that's equal to 2 times 9.81, so 19.62. There's a pushing force from the surface. And then last, there's the friction force that has to be in the opposite direction of the velocity. So that's along the surface this way. And the magnitude of that force is 0.1, that was our coefficient of friction, times whatever that fancy n is. So 0.1 times n. And that's it. So, Newton's second law says the weight force is 19.62 times the cosine of 240. 19.62 times the sine of 240. Plus 0n. And now that vector 0.1n, is that in the direction of positive x or negative x? Positive, yep. I mean, just look at, here's the coordinate system drawn here. So this is 0.1, you know, positive 0.1 times n, and then 0 for y. And the acceleration is, on the right side is the mass times the acceleration, which is a0. All right, so how are we going to solve this? Well, let me calculate that vector first, and then we'll do it. Bless you. Okay, so this is negative 9.81, negative 16.99, plus 0n, plus 0.1n, 0, is equal to 2 times a0. Now this is two separate equations, so let me write down what we have. The x equation says negative 9.81 plus 0.1n is equal to 2a. All we want is this vector a0. We just want to calculate what that value of a is so we can plug it in. So at first you might think all we need is that x equation, but notice that when we write out that equation, there's two variables in there, n and a. And you can't use one equation to find two variables, okay? And so we're going to have to use the second equation too and solve it as like a system. So the y equation says negative 16.99 plus n is equal to 2 times 0, or 0. And once you do that, the order for solving this is always the same. Use the y equation to solve for n, and then plug n into the x equation. So the order that you do this always is use the y equation for n, then plug n into the x equation for a. Okay, so the y equation says n is equal to 16.99. Do the algebra. Then the x equation says negative 9.81 plus 0.1 times what we get for n, which is 16.99, is equal to 2a. And so a is equal to negative 4.06 meters per second squared. Okay, well, we want the acceleration vector, so now let's plug this back in. Our acceleration vector is negative 4.060. And if we want to visualize it, is that up or down the ramp? Let's see. That is down because our positive x-axis is up the ramp. Okay? So a negative means the other direction. And so this is an acceleration that way at 4.06 meter per second squared. Now, the last question I asked was, is it speeding up or slowing down? We know that the velocity is down the ramp. We just figured out that the acceleration is down the ramp. So which one is it? Speeding up, exactly. So the velocity is this way. The acceleration is this way. So it's speeding up.
Wait, what'd you get for acceleration again?
Negative 4.06 for A.
Okay.
Any other questions? Okay, so we're going through this list of these 3 specific sort of approaches for different kinds of problems. I'm going to do an example now where I combine 2 of these kind of problems. So let's say that we have a ramp and we have these 2 carts that are connected by a cable. Let's say this one's 3 kilograms, this one's 2 kilograms. And we're going to pull here with a force of 15 newtons. And we want to calculate first the acceleration vector, and second, the tension in that cable. Okay, so this is combining both of the two specific cases that we've done so far. These two things are connected, and they move as a single object. They have the same acceleration. So do you remember the approach for things that move with a single acceleration?
You join the mass.
Yeah, so the first step is that we isolate the whole thing as a system, and we'll do that to calculate the acceleration, and then we'll go and isolate the individual bodies, okay? So we know we're gonna do that, and now we also know that we are going to use a rotated coordinate system with the y-axis pointing that way and the x-axis this way. Let's figure out that angle first for the coordinate system. Oh, I didn't give an angle yet. Let's say this is 10 degrees. The weight force vector is like this. From the positive x-axis to the vector is like that. So is it 270 plus 10 or 270 minus 10? Plus, yep. So 270, freeze. (270 plus 10 degrees or 280 degrees. Okay, so now free body diagram of the whole system. You definitely don't have to put this much effort into the outlines, but I'm just trying to be extra clear about what we're looking at. So there is the closed outline of the whole system. There's a weight force. The total mass of the system is 5 kilograms, so the weight force is 49.05. And now we'll go around the boundary looking for contact. That 15 Newton force is applied over here. And then the only other place where the surroundings contact the boundary is at the wheels. So I'm gonna just lump it all into one spot, and I'm gonna say this is the force normal total. And we don't have to worry about that cable tension because all of the stuff with that cable is inside our system. So Newton's second law says that 15 is in the negative x direction. So negative 15, 0. The normal, like always, is in the positive y direction. The weight force is 49.05 times the cosine of 280 degrees. 49.05 times the sine of 280 degrees. And that's all three forces. And this is equal to the mass of the system times A0.
Why is the 15 negative?
Because if you just look at the orientation of the x-axis, that force is in the opposite direction. Okay, I'll rewrite this one more time. So negative 15, 0, plus 0 in total, plus 8.52, negative 48.30 is equal to 5 times A0. The X equation then says negative 15 plus 8.52 is equal to 5A. And so A is equal to negative 1.30. We always want the acceleration vector, so now we'll plug this back in and we get that the acceleration vector is negative 1.30. Or, in other words, it's in the negative x direction, which is up the ramp. With a magnitude of 1.30. Do we know whether this is speeding up or slowing down? We don't, because we don't know anything about the velocity. Yep. Yeah.
And how do you go from positive direction to the 1.30?
Oh, well, so remember that negative is just a direction. So this is saying that the magnitude is 1.3 and it's pointing in the direction of negative x. And so just look at the direction of the negative x and you can see that negative is up the ramp. All right, well, that's not the end of this question because we also want to calculate the tension in the cable. So now I'm going to do a new free body diagram. And which one of these do we want to isolate in order to calculate the tension in that cable? What?
3 kilograms?
That'll work fine. The 2 will work fine. You'll get the same answer in either case if you do it right. Okay? But it's a little funny that that's true. A little mind-bendy, because if we isolate the 3 kilogram, we're going to put this 15 Newton force in the free body diagram. If we isolate the 2, we're not going to put that in. So like, how does it know? It's like power from beyond the grave, like hell, you know what I mean? Okay, so let's isolate this one. Then I'll isolate this one, just if we would have done that instead. We'll get the same answer, and then we'll talk about why that is. So I'll do the 3. And so acting on the 3, we have the weight. That's equal to 3 times 9.81, 29.43. And we have that 15 acting over here. Then we have a pushing force from the ground. I'll give that the variable name N3. And then the last one is the cable is pulling on it. And the rules for a pulling force are parallel to the cable, away from the body. Ah. Okay. I don't have to calculate the angle for the weight again. That's the same angle that we had before. So I'll go right to Newton's second law. And that says negative 15, 0, plus 0 and 3, plus 29.43 times the cosine of 280, 29.43 times the sine of 280, plus T0 is equal to the mass times the acceleration. And this time the acceleration we can just substitute in the vector that we calculated. So 3 times negative 1.300. I'll rewrite this. Negative 15, 0, plus 0 and 3, plus 5.11, negative 28.98.
Wait, how do you know tension's gonna be on the X
Because you just look at where that cable connects to the body that you're, and then think of the rules of pulling forces. So you know it's going to be at this point. You know it's going to be parallel to that cable and away from the body. Yeah. Okay, 1, 2, 3, and then we have the cable force like that. And then 3 times negative 1.30, 0. All we want is that value of t. So all we need here is the x equation. And it says negative 15 plus 5.11 plus t is equal to negative 3.90. And so T is equal to 5.99 newtons.
Did you get negative 3.1?
That's 3 times 1.30. Any questions about that? Okay, so now what if after the first step we had isolated the 2 kilogram card instead? We know that these cables always have to have the same tension everywhere along them, so we need to get the same answer. Let's make sure that we do. So free body diagram of the 2. There's a weight force down of 19.62. There's a pushing force from the incline that I'll call N2. And then the only other place where the surroundings contact the boundary is where the cable touches the left side. And so the pulling force is parallel to the cable, away from the body. And I'll call it T, but we're going to calculate that T separately. And so Newton's second law says that T is in the negative x direction. So we have negative T0 plus 0N2 plus 19.62 times the cosine of 280 degrees. 19.62 times the sine of 280 degrees. And all this is equal to what we would have known from the first step. Well, we have the mass of our body times, we would have already calculated the acceleration as negative 1.30, and then 0. So let me write it out again with this weight force calculated. Negative T0, 0N2, so this comes out to be 3.41, negative 19.32, and that's equal to 2 times negative 1.300. That's negative just because that's what we calculated in the first step. And then the x equation says negative t plus 3.41 is equal to negative 2.60. And so T is equal to, this time, I mean, there's a lot of places where I rounded off, so we have some round off error in here, but this comes out to be 6.01 newtons. So this is the same as the other answer. Except for, a small amount of round off error. Okay, so I asked this question before, like, how does it know? Like, how is it that this cart 2 knows that there's that 15 Newton force? You know what I mean? Because it doesn't appear here. How does it come into the math?
Is x greater than a?
Exactly. That's exactly it. So remember that 15 appeared in the first step when we calculated the acceleration. And then so anywhere that acceleration we carry it to has that information kind of in it. Okay. Yeah. All right, any questions about this? Hopefully that'll help with that question on the weekly assignment. And remember that there's no new lab this week. If you want to come work on labs or if you want to come work on homework and ask questions or anything like that, I'll be in there for that. And then, yeah, lab exam, I think I already said that at the start of class, is next week in lab.
Thank you.
Thank you.